In this video, we're going to derive the Friedmann equations, which are the equations that describe the expansion of the universe. And then we'll interpret them to understand various models of how the universe could expand. So we're going to cover a lot of topics in this video. First, we'll do a quick review of the FLRW metric and perfect fluids. Then we'll derive the Friedmann equations. Then we'll see how the universe behaves when it's dominated by matter, dominated by radiation, and dominated by dark energy, and why energy is not conserved in an expanding universe. Then we'll consider multiple different types of universes that the Friedmann equations describe, such as static universes, universes that expand and then contract in a big crunch, universes that expand but decelerate, and universes that expand and accelerate, which leads to the so-called heat death of the universe. Then we'll talk about which model best describes our universe. So remember, we're assuming our universe is spatially homogeneous, meaning it looks the same at all points, and spatially isotropic, meaning it looks the same in all directions. We found three possible geometries that meet these criteria, which are the closed or spherical universe, the flat universe, and the open or hyperbolic universe. After using a clever change of coordinates, we were able to write down all three metrics for these universes in a unified way, using a parameter k, which is either +1, 0, or -1, for closed, flat, and open universes respectively. We also have a scaling function a of t, which allows the spatial scale of the universe to change over time. Also, we're going to denote the derivative of a with respect to time as a dot, and the second derivative of a with respect to time will be denoted a double dot. We also calculated all the necessary curvature tensors related to the FLRW metric in the video Relativity 110c. We also said that the matter and radiation in the universe can be described by the energy momentum tensor for a perfect fluid, which has uniform energy density ρc² and uniform pressure P in all directions. These can change over time, but they're uniform over space for a homogeneous and isotropic universe. And this tensor's components are measured in the cosmic rest frame, which is the unique frame of reference where the cosmic microwave background radiation has no redshift, and where the average velocity of matter at large scales is 0. Also, in this video, I won't worry too much about the difference between mass density and energy density, since they are related by the constant factor of c². To get the Friedmann equations, we just have to dump all this information into the Einstein field equations. I'm using the mostly minus metric convention, so my cosmological constant term has a minus sign in front, and the energy momentum tensor has minus signs on the spatial diagonal terms. But the resulting Friedmann equations will look the same regardless of the metric sign convention that you use. The first Friedmann equation comes from the 0,0 component of the Einstein field equations, and the second Friedmann equation comes from the trace of the Einstein field equations. Let's start with the first equation. So we have our FLRW metric, the energy momentum tensor for a perfect fluid, the 0,0 component of the Ricci tensor, and the Ricci scalar. Now we write out the 0,0 component of the EFEs. We can plug in R00, R, G00, which is just +1, and T00, which is just ρc². We can simplify things by multiplying and dividing the first term by a, which will give it a common denominator with the second term. In the second term, we can simply do 1/2 times 6 to get 3. And on the right-hand side, we can cancel 2 powers of c. The first two terms now have a common denominator, so we can cancel the first term with the a double dot term in the second term. I'm also going to multiply and divide the cosmological constant by c², which lets us cancel c² in all the denominators. Then we'll move the cosmological constant term to the other side, giving it a plus sign. Then divide both sides by 3, and this gives us the first Friedmann equation. The second Friedmann equation is obtained by taking the trace of the Einstein field equations, which means summing all the terms with the inverse metric. The inverse metric raises an index on the Ricci tensor and on the energy-momentum tensor. In the middle terms, the metric and inverse metric cancel to 4x4 Kronecker deltas. The trace of the Ricci tensor is the Ricci scalar, and the trace of the energy-momentum tensor is the T scalar. And since the Kronecker deltas are the 4x4 identity matrices, this trace is just the number 4. 1/2 times 4 is 2, and r minus 2r is negative r. We can now plug in the Ricci scalar, and the trace of the perfect fluid energy-momentum tensor is rho c squared minus 3p. We can cancel these minus signs and distribute, multiply all terms by c squared, and divide all terms by 6 to get 4/6 and 8/6. Now, this term with a dot squared and k is exactly the left-hand side of our first Friedmann equation, so we can replace it with the right-hand side involving rho and the cosmological constant. We can then move the rho and cosmological constant terms to the other side of the equation. Here, minus 1/3 plus 2/3 gives plus 1/3, and negative 8 pi g over 3 plus 4 pi g over 3 becomes negative 4 pi g over 3, and we can factor that out of the rho and pressure terms. And the result is our second Friedmann equation. So we have the two Friedmann equations. The first tells us about the universe expansion rate, a dot, and the second tells us about the universe expansion acceleration, a double dot. As an aside, there is another equation related to the expansion of the universe, which is sort of like the third Friedmann equation, but it doesn't have an official name as far as I know. You can pause if you want to see the details, but we get this by taking the derivative of the first Friedmann equation and then substituting in the second Friedmann equation. This equation tells us how mass density changes over time as the universe changes size. Unsurprisingly, as the universe gets bigger with positive a dot, the mass in the universe gets less dense, so the result is a negative rho dot. There are actually two other ways to derive this third Friedmann equation. One other option is using the first law of thermodynamics, where we assume the universe expands adiabatically, meaning no heat is transferred into it. We can also derive the third Friedmann equation using the local conservation of energy law, which says that the covariant divergence of the energy-momentum tensor is 0. So there are many ways to arrive at this equation, but the equation basically encapsulates how local conservation of energy works in a universe with a changing spatial scale. Before we start looking at different possible models of the universe, let's quickly look at the behavior of universes that are dominated either by matter, radiation, or the cosmological constant, also called dark energy. These are defined by the W parameter from the equation of state we talked about in Relativity 110e, which is a relationship between the energy density of the universe and the pressure in the universe. Matter has W equals 0, since dust-like matter exerts no pressure. And the only non-zero component of the energy-momentum tensor is the energy density. Radiation has W equals 1/3, because we showed that the energy-momentum tensor for radiation must have 0 trace. And dark energy has W equals -1, because this turns the energy-momentum tensor into a constant times the metric, which is exactly what the cosmological constant term in the Einstein field equations looks like. If we take our equation for the rate of change of energy density and replace pressure using our equation of state formula, we can factor out rho and divide by rho, then integrate both sides to get ln rho and ln a with an additional constant of integration, k. We can then exponentiate both sides. E to the ln rho just becomes rho, and we can take this additive term and turn it into a multiplicative constant using exponent rules. Also, the exponent of a product can be rewritten as repeated exponentiation, so e to the ln a becomes a. And this gives us an equation for the energy density of the universe in terms of the universe's scale factor a. And we can combine all of these constants together into a new k constant in front. So given our three types of universes, if we sub in W equals 0 for matter, we find that mass density is proportional to a to the negative 3. And this makes sense. If we make the universe twice as big, the universe will become half as dense in all three spatial dimensions. So this negative 3 exponent is really telling us that the mass density changes inversely with the scale factor in all three spatial dimensions. For radiation, which has W equals 1/3, we find the energy density is proportional to a to the negative 4. With radiation, not only does it become less dense due to the expansion of the three spatial dimensions, radiation waves also get stretched out in the cosmic rest frame due to cosmological redshift. When the universe expands by a factor of a, the wavelength of light also increases by a factor of a. This means the frequency decreases by a factor of a, and by Planck's relation, the energy also decreases by a factor of a, which is why we see energy proportional to a to the negative 4 for radiation. The energy density changes with a power of negative 3 for the three spatial dimensions, and an extra negative 1 power for the energy lost due to cosmological redshift. Finally, dark energy has W equals negative 1, and we get that the energy density of dark energy doesn't depend on the scale factor at all. Dark energy is just a constant property of empty vacuum space itself. It doesn't matter how big or small space gets. 1 meter cubed of space will always have a constant amount of dark energy. So increasing the size of the universe fundamentally increases the amount of dark energy. And decreasing the size of the universe fundamentally decreases the amount of dark energy. Now, for matter, since energy density is proportional to the inverse cube of A, the total mass energy is conserved as the universe expands. But with radiation, we actually lose energy in the cosmic rest frame as space expands. And for dark energy, we gain energy as space expands. Energy is not globally conserved in general relativity. According to a result called Noether's theorem, conservation of energy is a law that only holds true globally if the universe is invariant under time translations. But if the universe's scale is changing over time, we don't have time translation symmetry, and there is no resulting conservation of energy law. We do still have local conservation of energy, which is given by the covariant divergence of the energy momentum tensor being 0 at a specific point. But we can't extend this law globally to all of spacetime. Basically, the cosmic rest frame is really a collection of individual frames all over the universe, and we can't directly compare the energy measured in one frame to the energy measured in another frame. Moving from one frame to another requires parallel transporting the frame across curved spacetime, and there is no unique way to do this in curved spacetime. If we parallel transport a frame to the same destination using two different paths, we get results that are different. So we can't meaningfully compare energies at different points in spacetime, and this means that we can't define a global law of conservation of energy. Now, let's look at the different possible universes that evolve according to the Friedmann equations, which are the equations that determine the behavior of a homogeneous isotropic universe over time. It's important to note that all these parameters, mass density, pressure, curvature, and the cosmological constant, must be determined by experiment. Now, no matter what values we plug in, we will get results for the universe's expansion or collapse that are consistent with general relativity. However, if we plug in values that don't match up with reality, the universe modeled by the equation won't reflect our universe in real life. With that said, for the rest of this video, I'm going to explore different kinds of universes that could arise based on the Friedmann equations. Not all of them will necessarily match up with our universe, but looking at different possibilities can help give us a feel of what the Friedmann equations mean. To start, let's look at Einstein's static universe from Einstein's 1917 paper. We know that our universe is expanding from observations of cosmological redshift, which tell us that distant galaxies are moving away from us. But the Friedmann equations can tell us what a static universe would look like. A static universe doesn't change size over time, so A dot and A double dot would both equal 0. From the second Friedmann equation, after some manipulation, we get an equation telling us the value of the cosmological constant in terms of the universe's mass density and pressure. From the first Friedmann equations, we set A dot to 0, and we can plug in our formula for the cosmological constant. We end up with a formula for the curvature k in terms of mass density and pressure. So these formulas are true for a static universe, and Einstein's static universe from his 1917 paper also had 0 pressure, so this simplifies the formulas even further, so that they're all equal to each other. So we know that the mass density ρ must be positive, which means everything else in this formula must also be positive, including the cosmological constant and the curvature k. We know that the curvature k only has 3 possible values, +1, 0, or -1. So since k is positive, that means it must be +1, meaning that the universe is spatially spherical. And if we go far enough in one direction, we'll end up back where we started. This also means the cosmological constant is inversely related to the square of the radius of the spherical universe. So Einstein's static universe is a universe with positive curvature and a positive cosmological constant. This is exactly what Einstein predicted in 1917. It doesn't match with observation, but it's impressive that Einstein could deduce the math correctly before the Friedmann equations were derived in 1922. Let's look at another early model of the universe, which is the de Sitter universe, proposed by Willem de Sitter in November 1917, just under a year after Einstein's paper on cosmology in February 1917. De Sitter proposed an alternative cosmological solution to the Einstein field equations where the universe is empty, and so the density and pressure are 0. For simplicity, we're also going to assume the universe is spatially flat, so the curvature k equals 0. De Sitter did not start with this assumption, but this will simplify our calculations. So in de Sitter's universe, mass density, pressure, and curvature are all set to 0. So the first Friedmann equation tells us that the ratio of A dot and A is the square root of the cosmological constant times c squared over 3. This ratio, A dot over A, is also the definition of the Hubble parameter h. In theory, the Hubble parameter could vary with time, but in de Sitter's universe, h is a constant. From basic differential equations, we know that when a function is proportional to its derivative, the solution is an exponential. So a de Sitter universe expands exponentially over time, where the exponential parameter is proportional to the square root of the cosmological constant. So we can see here that the cosmological constant has the effect of causing the universe to have accelerated expansion outward for all time. The second Friedmann equation doesn't tell us anything new, but the exponential solution we got is consistent with it. Now, even though our universe obviously has matter in it, the de Sitter universe can be a useful model for a universe that does have matter, but where the cosmological constant, or dark energy, heavily dominates to the point where the existing matter is negligible on cosmological scales. And since the most recent evidence says that the universe's expansion is accelerating, the mass density of the universe will become smaller and smaller over time, whereas the cosmological constant will remain the same. So as time goes on, in the far future, a de Sitter universe will be a good model for our universe when mass density becomes negligible on cosmological scales, compared to the cosmological constant. The ultimate fate of the de Sitter universe is for all mass and energy to be spread out more and more, causing the universe to cool more and more, until it basically approaches a density of 0 and a temperature of absolute 0 as well. This ultimate fate is called the heat death of the universe. It turns out we can also get de Sitter universes for k equals -1 and +1. Even though these solutions look different, they actually describe the same de Sitter universe where we've chosen coordinate systems with spatial slices that are either open, flat, or closed. So the de Sitter universe we just described was an empty universe with a positive cosmological constant. We could also ask what an empty universe with a negative cosmological constant looks like. This is called the anti-de Sitter universe. So looking at our first Friedmann equation with 0 density, we get this equation. If we try the case with k equals 0, because the cosmological constant is negative, this solution involves the square root of a negative number, so the solutions are imaginary. Scaling the universe's metric by an imaginary number doesn't make sense, so the solution is not physical. For k equals +1, we also get negative numbers under the square root, so we ignore this solution as well. For k equals -1, we actually get real solutions, where the scale factor is sinusoidal. You can pause and look at the proof here. So just as a positive cosmological constant causes the universe to accelerate outward, a negative cosmological constant causes the universe to accelerate back inward and collapse to a single point, in a so-called big crunch, where the scale factor becomes 0. Now, the physical interpretation of this first half period of the sinusoid is obvious. But when we reach a negative scale factor, the interpretation is less clear. It could mean that the solution is not physical, or it could mean that the universe will continue in an infinite cycle of big bangs and big crunches. But I'm not going to speculate about this here. In the Relativity 110b video, we talked about homogeneous and isotropic spaces for 3 spatial dimensions, determined by k equals +1, 0, or -1. And these were the spherical, flat, and hyperbolic spaces, and they each had a constant Ricci scalar everywhere. In the same way, we can now consider spacetimes that are homogeneous and isotropic, not just over space, but over time as well. So the universe appears to be the same at all times, and the future looks the same at all times, and the past also looks the same at all times. These correspond to empty universes with a cosmological constant that's positive, 0, or negative. These are called the de Sitter, Minkowski, and anti-de Sitter universes. And again, each one has a constant Ricci scalar. So for example, the de Sitter universe is expanding exponentially, and the rate of expansion is always proportional to whatever the current size of the universe is. For this reason, all times in the de Sitter universe appear identical. There's no way to tell how old or how new the universe is just by looking at the current time. And just as we can model 3D spherical and hyperbolic spaces by using surfaces in 4 dimensions with a constant radius or curvature parameter, we can also model the 4D de Sitter and anti-de Sitter spaces by using surfaces in 5 dimensions with a constant curvature parameter. I'm not going to go into the mathematical details here, so check the description for links to more info. Now, before we continue talking about more possible universes, I'm going to introduce some definitions and quantities that will help us understand the universe's evolution. So we already know that k equals +1 for a closed universe, k equals 0 for a flat universe, and k equals -1 for an open universe. Here, k equals 0 is the crossover point between closed and open universes. We can see what constraints this crossover point places on the universe's density. The crossover density between closed and open universes is called the critical density, denoted by rho subscript c. We'll also define the density parameter omega mr as the ratio of the actual density and the critical density. The m and r subscripts refer to the fact that the energy density could be due to matter m or radiation r. To define the critical density, let's take the case of a flat universe with k equals 0, and with no cosmological constant, so lambda equals 0 as well. Taking the first Friedmann equation and cancelling these terms out, we can rewrite this ratio between a dot and a as the Hubble parameter h of t, although we will often just write it as h. Solving for the critical density, we get 3h² over 8 pi g. The corresponding density parameter rho over rho c equals this. We're going to see that the overall shape of the universe, being closed, flat, or open, will depend on how the actual density of the universe compares to this critical density quantity. Looking at the first Friedmann equation again, we can rewrite the fractions and then bring the curvature term to the other side. We can then rewrite a dot over a as the Hubble parameter h, then divide all terms by h². We see that the first term on the right-hand side is our density parameter. We're also going to define these other two terms as the dark energy parameter omega lambda and the curvature parameter omega k. So this is an alternative way of writing the first Friedmann equation, where these three parameters sum to 1. So knowing any two of them will automatically determine the third. Since we want to examine the relationship between density and curvature, let's look at the case where the cosmological constant is 0. So our first Friedmann equation can be rewritten like this. We can now look at the cases of the density being less than, equal to, or greater than the critical density, and see how this affects the curvature of the universe. For density less than rho c, the density parameter is less than 1, and the left-hand side becomes negative. Since the right side of the equation has a² and h², which must be positive, the only way to make the right-hand side negative is by choosing negative k, meaning we have negative curvature or an open universe. If rho equals the critical density, omega equals 1, forcing both sides to equal 0. So with k equals 0, the universe is flat. And for rho greater than rho c, omega is greater than 1, so both sides are positive, and we get k equals +1 for a closed universe. So we see that when the cosmological constant is 0, the density of the universe directly determines the universe's curvature. So the Hubble parameter h and density parameter omega can tell us about the universe's shape, but they can also tell us about the general evolution of the universe's scale factor a over time. Loosely speaking, h tells us about the slope of the scale change, and omega tells us about the overall behavior of the scale change. The first thing to note is that since density and pressure are always positive, and we're assuming for now that the cosmological constant is 0, the second Friedmann equation tells us that a double dot is always negative. So the universe's expansion is always decelerating. The second thing to note is that if we take the first Friedmann equation with lambda equals 0 and rearrange, we get a term with density times a squared. Recall that for matter-dominated universes, density evolves as a to the negative 3, and for radiation-dominated universes, density evolves as a to the negative 4. So in this term, rho will always overpower the a squared. And as the universe gets bigger and bigger, this term will go to 0. We can prove this mathematically here. So in an open universe that's expanding, this term will eventually go to 0. But since k equals -1, this positive c squared term will always stick around. So in this case, the universe starts off expanding fast, then decelerates, and in the far future, where the density approaches 0, the expansion reaches a constant expansion rate of c. For a flat universe, an expanding universe will eventually send this term to 0. And since k equals 0, this term doesn't exist. So in the long term, we end up with an a dot of 0 and an a double dot of 0. So an expanding flat universe in the far future will tend toward a maximum size that it can never expand beyond. For a closed universe with k equals +1, since we have both positive and negative terms here, it's actually possible for the right-hand side to equal 0. This means that we can start off with an expanding universe, hit a maximum a scale value with a dot equals 0, and then a dot will change sign and the universe will start contracting again. Since a double dot is always negative, this contracting universe will contract faster and faster until the size reaches 0, which is the so-called big crunch. So for a 0 cosmological constant, an open universe's expansion will slow down to a value of c. A flat universe's expansion will slow down to 0, reaching a maximum size, and a closed universe will expand to a maximum size, then shrink back down to nothing in a big crunch. These three cases are also determined by the density parameter. The Hubble parameter h determines the slopes on these curves, with larger h giving steeper slopes. Now, all of this is with a cosmological constant equal to 0. So what if lambda is non-zero? Going back to our first Friedmann equation, this means that the density parameter, dark energy parameter, and curvature parameter all sum to 1. So knowing any two of them will determine the third. For example, if we look at the sum of the density parameter and dark energy parameter, by checking if it's less than, equal to, or greater than 1, we can determine if k is -1, 0, or +1. But what about the evolution of the universe? Well, if the cosmological constant is negative, the answer is easy. The second Friedmann equation has a portion involving density and pressure that's less than or equal to 0 by default. So a negative cosmological constant just guarantees that a double dot is negative for all time, meaning the universe expansion is always decelerating. So regardless of the universe's spatial geometry, the universe will always expand and then contract back down in a big crunch when the cosmological constant is negative. What about a positive cosmological constant? Looking at the first Friedmann equation, these terms are greater than or equal to 0. And if k equals 0 or -1, this term is also greater than or equal to 0. This means A dot squared is always positive, and so A dot is never 0, so it can never change sign, meaning A dot itself is always positive. So the universe is always getting bigger. And as the universe expands, the density and pressure go to 0. So while the acceleration is initially determined by density and pressure, as time goes on, the acceleration will be determined only by the cosmological constant, and A will increase exponentially. So with a positive cosmological constant and k equals 0 or -1, the universe evolution looks like this: decelerating when density and pressure dominate, but accelerating when the cosmological constant dominates. The case with positive cosmological constant and k equals +1 is more complicated. Because the curvature term is now negative, this means A dot squared can be 0, and so A dot can change sign. Although whether the sign change actually happens depends on how large the density and cosmological constant are. We know for the Einstein static universe, the cosmological constant exactly balances with density, and we get a static universe that doesn't change over time. However, if density is just a bit larger, the universe will contract in a big crunch. But if the cosmological constant is a bit larger, we'll eventually get accelerated expansion off to infinity. A summary of all the universe evolutions for each combination of k and the cosmological constant are given here, based on a figure in Lambourne's textbook. So with all of that said, out of all of these models, which describes our universe? Well, since 1998, we've known that the rate of galaxies receding away from us is accelerating, indicating a positive cosmological constant. Also, by examining the geometry of hot and cold spots on the cosmic microwave background radiation, we can determine the overall curvature of the universe. Multiple experiments have measured that the universe is very close to being flat, so we'll take k equals 0. As we've already seen, a flat universe with positive cosmological constant evolves like this, starting with a big bang, followed by deceleration, then transitioning to acceleration. The CMB radiation is leftover evidence of an early universe dominated by radiation, where energy density changes as a to the -4 and lambda is negligible. Solving the Friedmann equations gives us a scale factor that grows with time to the power of 1/2. Since radiation loses energy density very quickly in an expanding universe, matter eventually ended up becoming the dominant form of energy density. In a matter-dominated universe, energy density changes with a to the -3, and lambda is negligible. This gives us a scale factor that grows with time to the power of 2/3. As the universe expands, the energy density of matter continues to decrease, and we transition to a universe where the cosmological constant, or dark energy, dominates, and the universe grows exponentially. So this is a bit simplified, but generally speaking, this is a good approximation of our current knowledge of the history of the universe. If we were to draw this timeline to scale, it would look like this. We currently live in an era where the current composition of the universe looks like this, dominated by dark energy. Also, I'll mention that the extremely early universe in the first fraction of a second is hypothesized to have undergone a period of extremely rapid expansion called cosmic inflation. I'm not going to discuss inflation, but you can check the description for links to more information on it. So for a quick summary of this video, the assumption of a homogeneous and isotropic universe leads naturally to the FLRW metric and a perfect fluid model of energy and momentum densities. Plugging these into the Einstein field equations gives us the Friedmann equations, which govern the expansion of the universe. And analysis of the cosmic microwave background radiation and the redshift of distant galaxies has helped us estimate these parameters and come up with a model of the history of our universe. So this is the last video I plan on making in my Relativity series. I hope you enjoyed it, and I'll leave some links in the description on further topics that I didn't cover.